Hello, my name is Robert Zhang, and my partner is Surui Wang, and today we'll be presenting our GPU architecture semester project, optimizing data transfer through CPU compression and GPU decompression. Because of the processing power that GPUs have for parallel computations, GPUs are now ubiquitous for more than just graphics processing. In this paper, we investigate optimizing the traditional host device model of the GPU, where the host offloads data to the device for processing. Because of this heterogeneous design, the CPU and GPU must transfer large amounts of data, and there's room for optimization in this data transfer. The PCIe, or Peripheral Component Interconnect Express, is a high-speed interconnect bus used in a variety of situations, including connecting a network interface card to the CPU. Here, the PCIe connects the GPU together and the CPU to the GPU cluster. The PCIe can transfer data at a high rate depending on the version of the PCIe. For example, version 2.0 can transmit a total of 16 gigabytes per second, while version 3.0 can transmit 32 gigabytes per second. Now, this may seem very high, but they are the ideal transmission rates, and research has shown that the PCIe interconnect can still be a bottleneck for runtime because of the amount of memory copies needed in some applications. NVIDIA research has developed a specialized communication link known as NVLink that boasts much higher transmission rates than the PCIe. However, NVLink is still a constantly changing technology that still requires the use of PCIe under certain situations, such as when multiple GPUs are set up together, as shown in the figure to the right. And therefore, we decided to focus on the data transfer through the PCI bus for our experiments. Now, in order to prevent PCIe from becoming a bottleneck during the application's runtime, we attempt to use a basic lossy data compression algorithm to reduce the size of the data before it passes through the interconnect. So for our experiments, we utilize CPAC compression on the CPU side, and then we modify the CPAC decompression code for the GPU side. And then after that, we evaluate the effect of this encoding and decoding on a vector add application's runtime. My partner will now discuss the algorithm that we use for our experiments as well as the results.
We will be using in our project is called CPAC. CPAC, short for Cache Packer, is a lossless compression algorithm designed specifically for high-performance hardware-based on-chip cache compression. However, to meet our request, which is the GPU-based vector addition application, we need to do some adjustments. The number one adjustment is to change the input from cache data into vectors, and this can be done very easily. The other adjustment is about parallelism. We can do that by separating the data into blocks and do compression or decompression on each block in parallel. These two figures shows the algorithm of CPAC in doing compression and decompression. In these two figures, we use an input of 2 words per cycle as an example. However, the algorithm can be easily extended to cases with 1 or more than 2 words per cycle. For the compression part, during one iteration, each word is first compared with patterns ZZZZ and ZZZX. If there is a match, the compression output is produced by combining the corresponding code and unmatched bytes as indicated in the table that we will represent later. Otherwise, the compressor compares the word with all dictionary entries and finds the one with the most matched bytes. The compression result is then obtained by combining code, dictionary entry index, and unmatched bytes, if any. Words that fail pattern matching are pushed into the dictionary. And for decompression, the decompressor first reads compressed words and extract the codes from analyzing the patterns of each word, which are then compared against the codes defined in the table that we have just mentioned. If the code indicates a pattern match, the original word is recovered by combining zeros and unmatched bytes, if any. Otherwise, the decompression output is given by combining bytes from the input words with bytes from dictionary entries. if the code indicates a dictionary match. On the right-hand side is the table that we have just mentioned. This table summarizes the patterns and the coding schemes used by CPAC. And at the bottom, there are some compression examples for different input data. When there's an input, we first look them if they match the pattern ZZZ and ZZX or not. If yes, we'll look up the code table and combine the code with our match bytes. If the input does not match the pattern ZZZ and ZZX, we then look at them to see if they match the bytes in dictionary entries. If no, we look up the code table and combine the code with our matched bytes. If yes, we look at the code table, look at the dictionary entry index, and combine the code with our matched bytes. And this is how CPAC works. With CPAC in mind, we perform several experiments. The experiments are performed based on the vector addition application. The application goes like this. We first do the initializing the two vectors on the CPU side. Then we compress the two vectors on the CPU side, and then we transfer the data from CPU to GPU and decompress it on the GPU side. Then we do calculation, which is calculating the sum of those two vectors on the GPU side. And after we get the results, we compress the results on the GPU side and then transfer the compressed data from GPU to CPU. Then the CPU will do the compression and get the original results. And finally, we do the validation. The vector size is set to 10,000, and the block size for compression are being set to 32 or 64 or 128 or 256 bytes. As for the results, we first look at the compression rate on different block sizes. It is very surprising for us to see that the compression rate are rather high in our applications. And as for block size which is very small, in our case which is 32 bytes, the compression rate can sometimes actually be more than 1. And as the block size keeps increasing, the compression rate will decrease. Then we look at the time consumption of each application. There are 5 applications, the original, and 4 CPAC with 4 different block sizes. We can see that the original application has the least time consumption, which is quite surprising. And with CPAC, the time consumption are always higher. When the block size gets larger and larger, the overall time consumption also gets larger and larger. But when we look at the orange bar, which refers to the data transferring time, it decreases when the block size increases. However, it doesn't decrease that much comparing to the compression and decompression time. So based on all these results, we can have these conclusions. The first one is the compression rate for our application is rather high and therefore cannot accelerate the whole process. The second one is when the block size gets bigger, the compression rate drops, but the compression time and the decompression time increases. The third one, when the block size is too small, the compression rate can actually get larger than 1. And the fourth, the overall time consumption keeps increasing when the block size increases, and the lowest time consumption comes from the original application with no CPAC. And finally, we think other applications with larger input size and less randomization will benefit more from CPAC. And that's all. Thank you.